Let us now study about longitudinal magnification by spherical mirrors. This is the magnification along the principal axis for an object size. Say, to understand it better, we consider a concave spherical mirror. And say this is the principal axis of mirror, and at a distance x from the pole of mirror, an object is placed which is very small size, and say the thickness of this object is TO, and we wish to find the image of this object. And let us consider, by using mirror formula, we get the location of image is at a distance y from the pole of mirror. So this is the location where image is located. As we know, in case of concave mirror, if the object and image both are on the same side, they are real and the image will be inverted. So in this situation here, you can see if the object is AB, in this situation it is closer to mirror, the image if it is farther away, then the point which is closer to mirror will be away from it, because the point which reaches the focal point, the image will reach to infinity. So the image of A will be A prime and that of B will be B prime. And say the image thickness is Ti. If we wish to relate the thickness of image and object which are along the principal axis, if we talk about the height, we can easily correlate the two by using the magnification formula. Now in this situation, these are obtained by using mirror formula. So here we can using mirror formula, we have, if f is the focal length of the mirror, here we can use 1 by x plus 1 by y is equals to 1 by f. And in this situation, we have taken x as object distance u, y as image distance y. Now in this situation, we differentiate this expression just to find out the variation along the principal axis in values of x and y. So see what we'll be getting differentiating this expression. We get 1 by x, after differentiation it will be minus 1 by x square dx minus 1 by y square dy is equals to 0, as focal length always remains same. So from this relation we are getting dy by dx is equals to minus y square by x square. Here dy is the slight variation in y and dx is the slight variation in x. The ratio of these two is given as negative of y square by x square. So in magnitude, for small TO, which is the thickness of object, we can write dy is the small variation in y if TO is considered a small variation x. So here we can write Ti by TO is equals to dy by dx, and in magnitude we can write it y square by x square. And here y and x we can replace by v and u, which are considered as image and object distance. So this will be v square by u square, and the same can be written as square of the magnification. So here Ti we can write as image width along principal axis is equals to m square times the object width along principal axis. And here this m square we can denote it by another term ml, this is called longitudinal magnification, which is used for relating the small thickness of image and object along principal axis. And be careful, this is valid only when Ti and To both are very small compared to x and y, because we obtained this relation by derivative. So this is actually dy by dx, which is very small extension of y and x.